Now that we've learned the full expression for the gravitational force, let's learn the corresponding full expression for the gravitational potential energy. So our simple expression for force that we were using was force equals mg, and our simple gravitational potential energy expression was mg times the height above the ground. Now we've learned this more complete version of the gravity force, capital G times m1, m2 over distance squared between those two objects. And now the corresponding full expression for the gravitational potential energy looks like this: minus G m over r. Oh, sorry, m1, m2 over r. So there's a minus sign in here, and on the bottom you have r instead of r squared. So let's think about this expression and what it means. I'll just write it out here in equation form one more time. Gravitational potential energy is minus G times mass of first object, mass of second object, divided by the distance between them. And this minus sign and the fact that you have an r in the denominator means that we have now defined our 0 point of potential energy at a location r equals infinity. So the 0 you can see if you put r equals infinity here, this expression goes to 0. Before, when we used this expression for potential energy, we would define some height to be the 0 level, often ground level, and then we would measure potential energy relative to that height. We're doing the same thing here. We're just defining a certain position to be the 0 level of gravitational potential energy. And we're saying that position is when the two interacting objects are really, really far apart. So in physics, when we say infinity, I mean, infinity doesn't actually exist in nature. That's an abstract mathematical concept. Infinity really means that they're just far enough apart that the gravity force is small enough that it doesn't matter. So with this choice of 0 level for gravitational potential energy, that means that when objects get closer together, the change in gravitational potential energy is negative. So when r decreases, the change in gravitational potential energy is negative, which is what we're used to. If you have an object that's falling, we're used to saying that it has a larger potential energy at the start, a smaller potential energy at the end. The change in gravitational potential energy is negative. Oops. Where? And actually I meant to say when. When r decreases, change in potential energy is negative. Okay. And when that distance increases, the change in gravitational potential energy is positive. When you increase the distance between the two objects, there's more gravitational potential energy. That's the same thing we've always been doing. When you have an object and you raise it up above the Earth's surface, we say it has more potential energy. All we've done is increase the distance between the two objects, the pen and planet Earth. So let's apply these ideas in an example from the textbook. This is example 7 11, dealing with an asteroid that comes near the Earth. There have been lots of disaster movies about this scenario. What happens if an asteroid gets close to the Earth and it might crash into the Earth? That can be super damaging. So there's some movies that explore the scenario of moving an asteroid away before it crashes. So let's say that we have an asteroid of mass 10 to the 9 kilograms. And it comes from very far away, meaning its initial distance is infinity. And it falls toward the Earth. So let's answer some questions. First one is, what is the change in potential energy when it reaches a distance that's about equal to the distance of the moon's orbit? That is 4 times 10 to the 5th meters. Okay, just beyond the moon. So that change in potential energy is PE final minus PE initial, and now we use our new expression. M1 is the planet Earth mass, M2 is our asteroid mass. Okay, so final potential energy minus initial, but this initial potential energy is 0 because we started really far away, so our initial is infinity, so this whole thing goes to 0. So we just have this expression, and plug in the values. Remember, G is 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. M1 is the mass of planet Earth, 5.972 times 10 to the 24 kilograms. M2 is this value. Our final is this value. And we get minus 9.97 times 10 to the 14 joules. And again, that's negative because the objects are getting closer, so the potential energy has decreased. Okay, so how fast is that asteroid moving? In that scenario? Well, we can use conservation of energy, relate the change in potential energy to the change in kinetic energy, minus change in kinetic energy is negative 1/2 mv final squared minus 1/2 mv initial squared. We'll assume the thing started out stationary. And so we get this relationship that V final is negative 2 delta PE over M square root. And we can plug in that value, and you find that the speed is 1.41 times 10 to the third meters per second. So by the time this asteroid gets to about the same distance as the moon is, this 1 billion kilogram asteroid is moving over a kilometer per second. It is carrying a lot of kinetic energy. And in part C is my own question that I'm making up. I want to find out how much kinetic energy does this thing have if it reaches the Earth's surface, and how dangerous would that be? So what is the KE at the Earth's surface? We'll use our same approach. We got PE final minus PE initial equals negative KE final plus KE initial with those minus signs. That was 0. That was 0. And we find that this final kinetic energy is negative G times mass of Earth times mass of asteroid divided by the final radius, or final distance, which is the Earth's radius. It's now the surface of the Earth. Okay, so we get this thing, and you put in those values. It's about 6.3 times 10 to the 16 joules. So how big is that? Well, the atomic bomb that was dropped on Hiroshima in World War II was about 6.3 times 10 to the 13 joules. So this is 1,000 atomic bombs. So this is why you don't want an asteroid to hit the Earth's surface. Super destructive.